How's it going, guys? We're going to do this video on ellipses now. You should have already seen the circle one, and we're just going to continue conic sections. We're going to talk about the ellipse. And this one's a little trickier, but also very important. Let's go ahead and do the general form again, so you can see that the general form of a conic section, all conic sections, not just the ellipse, is this. This is going to be ax squared plus bxy plus cy squared plus dx plus ey plus f, okay, equals 0. That's your general form. And as I said, you can represent any conic section in this form. Sometimes the constants are 0, sometimes they're different numbers, but if you change these, these constants, like I say, they're constants or not, there's only one constant. If you change these coefficients, then you will get a different conic section. But more important than the general form in this case is the standard form. Extremely important because it tells you stuff. Okay, if I could write correctly, standard form. Okay, so here we go. This one is important. It's going to be this form: x minus h squared over a squared plus y minus k squared over b squared equals 1. Okay, that's kind of the general standard form. I shouldn't say general. This is just the standard form of the ellipse. So we have a standard form and a general form. That's what we're going to call them in class. Okay, for this class, that's what we're going to call them. So the center of the ellipse, it's just an oval shape as an ellipse, is the same as the circle. It's going to be situated at h and k. Not any different there. So what I'm going to do is I'm going to make up an example for you, and I'm going to draw it. Okay, I'm going to try to make it a little big so that we can kind of see what's happening. But we'll work that out. Let's see. If I want to make this fairly large, we'll try that. Okay, so I'm going to say x. I'm going to make up some numbers here. X minus 3 squared. Let's put that over 49. Make it large. Plus y plus 2 squared over 25. And this will always equal 1. So this standard form is always equal to 1. Okay? So the ellipse, let's put its center down on the graph. I'm going to actually graph this. The center is HK. So what is HK? The center, to find HK, you just look at this number and flip the sign. So this is going to be -3, and this is going to be -2. I'm sorry, it's going to be +3 and -2. So that's going to be 3 and -2. That's right here. That's the center of this graph. Okay? And what we're going to do is we're going to find the bigger of these two numbers on the bottom, and it's going to be this one. And we're going to say, okay, that's my a squared. That's going to equal 49. So the square root of a will be 7. Okay? So this is going to define my major axis. The longer of the two is the bigger number right here. So my major axis is going to be defined by that number right there, which is 7. It's going to be defined by a. So what I'm going to do, since it's underneath the x, I'm going to go parallel to the x-axis. I'm going to go from the center 7 to the right and 7 to the left. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okie doke. So right here, what I found, so this is my center. Actually, go be careful here when I draw this. 1, 2, 3. Okay, I'm not going to go too far. So the center is right here, and these are called vertices on the outside. These are vertices. Same thing right here on the outside, vertices. So those are the vertices. You'll be asked to find those, and they're always along the major axis. This is the longer of the two. So the major axis is important because if I were to draw from the center, that length is 7, and that length is 7. So the entire length of the entire axis, major axis, is 7 plus 7, which is 14. It'll be twice what this number is. So the major axis length, we'll call it, is going to be 2 times a. Okay. So let's go and talk about the minor axis now. Minor axis. So we have a minor axis to go with the major axis. There's 2 of them. And this will be defined by the smaller of the 2 numbers. Okay? And then we're going to say this is b squared is equal to 25. So b will equal 5. Okay? Technically plus or minus 5, but we're going to say it's 5. Okay, so that means from the center, since this is underneath y, we're going to go up and down from the center 5. So we're going to go up 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5 when I draw this. Okay, so we have this right here. That distance is 5. That distance is 5. And that's called your minor axis. That's the shorter of the two. And how you draw the actual ellipse, okay, is we're going to, let's get a color I can see, red, and then we're just going to draw out here as best I can, which won't be perfect at all, this sort of oval shape. And this is a horrible drawing because I can't freehand it very well, but that's what the ellipse looks like. It's an oval shape, okay? So here's the deal. In fact, all circles are ellipses. They're just a very specific type where the major and minor axis are actually the same. If this were 5 up and 5 out, up and down and left and right, it would be a circle. So when these axes are the same, these numbers on the bottom are the same, what you're looking at is actually a circle, because all circles are ellipses. They're just a special kind of ellipse where a squared and b squared are actually identical. They aren't in this case, so this is not a circle, but it still is an ellipse. Okay, so we have what do we have going on here? So we have the length of the minor axis. Call it the minor axis length. Will be 2 times b, whatever that is. So what I'm telling you is I'm saying 5 plus 5, so this distance would be 10. That would be the minor axis. So the minor axis length, I should actually put this in orange, for this will be, this will equal 14 for this. And for this one, it'll equal 10 for the minor axis, okay? So you might be asked for all those things. You're also going to be asked for the vertices right here on the ends. These are the vertices. And then these right here on the top and the bottom are not vertices. They're called co-vertices if they're on the minor axis. Co-vertices. Right here and right here. Those are co-vertices. So you could be asked for all those coordinates. Those are questions that are very common in pre-cal for conic sections. So I could say, okay, what are the vertice coordinates and the co-vertices? And I'd ask you questions like that. So the vertices right here, if this is centered at 3, -2, if I'm going along the x-axis, along the major axis here, okay, I'm going parallel to the x-axis, so I'm going left and right for the major axis. What is this coordinate? What is this coordinate? I'm just going to subtract 7 from this center x value, which is 3. So 3 minus 7, this will be -4. Okay, -4 and -2. Here it'll be 3 plus 7, which will be 10, -2. So those are the vertices right there. We're just adding and subtracting to the x coordinate of the center. We're just adding and subtracting 7 to that. So it's pretty straightforward. -4, -2, and 10, -2. What you notice, since the we're only moving along the x boundary there, that we're actually not really changing the y value at all. It's going to be -2 still and -2 for both. We're not going up and down. We're just going left and right. Not the same case for the vertices though. Here we are going up and down, so we're going to keep the x value of the center the same. It's going to be the same for both. But what's going to change is we're going to change the y value. We're going to say, okay, -2 plus 5 and -2 minus 5. So we'll do the minus one first. I always write the bottom one first. So -2 minus 5 is -7. That's going to be, sorry, 3 -7, not a -3. 3, and then get that marker going. 3 -7 right here. And this one will be 3. And then you'll have -2 plus 7. Or, sorry, plus 5. Yeah, plus 5, my bad. -2 plus 5, which is 3. So this is 3, 3. Okay, so that's what you have here. Vertices. Okay, vertices and co-vertices. You would be asked to find things like that. And I'm just kind of giving you all the little pieces here. Okay, so now into the hard part. Believe it or not, there's one more complicated thing. And this is this concept of what is called a foci. Okay, and foci, a focus is a singular point, and if you have more than one focus, it's called foci. It's plural, actually. Like this, foci. That's the plural of a focus. Okay, ellipses have more than one focus, so together they're referred to as foci. Only parabolas have one, okay? And circles, technically, but That's because it's the foci and the center are the same thing. But that's neither here nor there yet. So because you don't know what a focus is yet. So what a foci though, let's talk about that. They're actually used to draw the ellipse. They can be used to draw the ellipse. And I would love to show you how to do that, but I don't have a piece of string and a pair of pens to do this. So I will post a video of some other teacher. I believe he's from Europe somewhere, or Ireland, and he'll be drawing this. I'll post a video of him drawing one using the foci to draw the ellipse, but I don't really have the tools for that to do this on the screen here. So I'll post a video of somebody else doing it, but it's really neat to see. If I were in the classroom, it'd be easier because I could just write on the board with a piece of string, but I'll just post another video. So let me show you how it works though without actually drawing it. A focus is just a point on the major axis. So somewhere on the major axis here, there's going to be 2 points. It's going to be like right here and right here. I don't know where they are, I'm just guessing, right? But they are defined a very specific way. I told you the values of a squared and b squared. That's basically, this determines the major axis, this determines the minor axis. There's a distance here from these are called foci. 2 points on the major axis, right here and right here. And the distance from the center to that foci, or that focus, we'll call it, singular, is c. So here's how this works. C squared, that distance, is equal to a squared minus b squared. It's actually identical to the Pythagorean theorem, except it says minus instead of plus. That's how I remember it for the ellipse. Okay? When you start drawing hyperbolas, you'll find it's exactly the same as the Pythagorean theorem. It's just a squared plus b squared to find the foci for the hyperbola. But for the ellipse, it's a minus. So here's where we're going to find this distance c. So c squared is going to equal this a squared here minus this b squared. So it's going to be 49 minus 25. Okay? And that's going to give me 24. So c is going to equal the square root of 24. Okay? And really that's like saying 4 times 6 if you want, which is 2 root 6 if you want to call it that. That's fine. But you could call it root 24 if you want, or you can call it 2 root 6. Doesn't make a difference to me. But the coordinates now, this distance c is known. It's going to be root 24 and root 24 one way or the other. So I could actually write the foci coordinates, and I'm just showing you how to find them. And this will be, we're subtracting from the x to go back what? Root 24. So the x right here is 3, so it's going to be 3 minus root 24 if I don't rationalize it. And we're going to keep the y value the same at -2 because it's not going up or down. And then the other one's going to be 3 plus root 24 and then -2. So that's not going up or down either. So this is really how you find things. Now, how does that focus work? Well, technically how it works is this particular value c, which is root 24, which is just under 5, okay? Since root 25 is 5, we're just going to be a little less than that. So from the center, I'm going to go over just underneath 5 to the left. 1, 2, 3, 4, 5. I'm going to be just a little shy of 5 right there. I'm going to go 5 the other way as well. 1, 2, 3, 4, 5, but stop just a little short of it right about here. So this is actually about the true location of where my foci are. So that is that. So if I were to actually, conceptually, this is what I'm doing. If I were to actually put a piece of string and bolt it to the board there, to the grid, and then on both ends, these are the ends of the string, and I were to just pull it from the middle with a pin or something. So I will nail it to here and here on the foci, and then just pull it up with a pencil or pin and pull it as tight as I can. Pull it taut right here. That's where it'll end up at the co-vertex there. So basically what I'm telling you is if you were to pull it tight through the middle and just trace around with keeping the tension on the string, tracing it around the outside of the foci as far as you can stretch without breaking the string, you would actually create an ellipse if you were to draw this. So I'm going to post a video, I'm not with that, of somebody else doing that since I don't have a string. I can't show you that, but somebody else will do that. But another interesting property here though is that this distance right here is the same thing as the distance here, which is a, from here to here. This length and this length are the same, as it turns out. They're congruent. So what that means then is if this part of the string is also a, so this entire yellow string that I tried to put here, right? This yellow string that I put here is actually, if you were to lengthen it out, it would be the same length as the major axis as well. That's a property that's always true as well for the focus, right? So for the end of this and the end of this. So that might make more sense when you see the drawings done. So watch that video when I post it, but this is pretty much how an ellipse works. Okay, so this is about how all you'll be asked to find with an ellipse. This is how you draw an ellipse, and the foci have some properties that you'll see in the video on how to use the foci to actually draw the ellipse as well. Okay, so just remember this, the distance and the foci are always on the major axis, whether it be horizontal or vertical. The longer axis is the major one. Okay, all right, I appreciate you watching.